All right, so metals are found in combination with other elements, and we call these compounds commonly as minerals. Minerals usually contain some unwanted material like soil and cell particles with them. We call it ore. Ore is the form of metal which is combined with other elements and also with some unwanted materials. So there are very few unreactive metals such as gold, which are found in their actual state, silver, copper sometimes maybe. They're also found in their actual states. Now, most of the time when we are extracting the metal, they are present in their sulfide forms. For example, zinc is present in the form of zinc blende, which is ZnS. So what we do is that we go with a process by the name of roasting. Roasting is actually conversion of that sulfide ore by reacting in air filled with oxygen. Oxygen reacts with it, produces the metal oxide and also the sulfur dioxide. The metal oxide then can be used for the extraction of metal, and that depends upon how we can use it. There are a couple of methods that we can consider, but before we go with those methods, the main point is taking economic factors into account. Now, the cost of energy and the cost of reducing agent are one of the most important factors we need to consider when we are supposed to select a process for the extraction of metal from that specific ore. Now, as you can see, for the list or the part of the reactivity series given over here, you can see that the carbon is the only non-metal, hence written in brackets over here. So the less reactive ones than carbon are zinc, iron, and copper, which can easily be reduced with the help of carbon. The more reactive ones than carbon are all group 1 and group 2 elements, also including aluminum from group 3. So carbon cannot be used to reduce them from their oxides, but can be used for zinc, iron, or copper. So that's actually a decisive factor that we can use carbon for these. Iron is the most used metal. So we take the example of iron. The most common ore is actually hematite, and that is Fe2O3. So we are using this Fe2O3 over here. We are using carbon, and carbon can easily convert it into or reduce it into iron, which by this process melts. So that's why liquid iron, and carbon itself is converted either into carbon monoxide or carbon dioxide. We may even use carbon monoxide as the reducing agent. So we can both use carbon or carbon monoxide as reducing agents. And in that case, we'll get the same iron in liquid or molten form, but we're also going to get carbon dioxide. So we can reduce the oxides into pure metals by reacting either with carbon or with carbon monoxide. They act as reducing agents. Moving on, the process over here as shown in the blast furnace, we call the process of iron as blast furnace because we are going to heat it up to a pretty high temperature, hence the word furnace. We're going to use strong blasts of hot air, hence the word blast. As you can see, strong blasts of hot air are going from the downward sides all the way to upward direction and moving out as hot waste gases. And as also part of this upward portion of blast furnace, we can see we are getting the charge in. Charge is actually the raw material that you let enter into the blast furnace, that is iron ore, the formula of which is Fe2O3, coke, and carbon. Carbon is usually present in the form of coal when we take it in solid form. Coke is the form of coal that has been heated up to 100 degrees centigrade for a few hours. All right. Why do we do that? We do that because we have usually nitrogen, sulfur, phosphorus, and other non-metals present in coal. When we heat it for some time, the oxygen can convert N2 into its oxides, maybe NO, maybe NO2. sulfur into its oxide, maybe SO2, maybe SO3, and also phosphorus into its oxides, maybe P2O3, maybe P2O5. So these are the oxides which are usually in gaseous form and can easily leave the system except this or this one, which are liquid or solid. So gases can leave, hence increasing the percentage of carbon in coke. In the end, I was telling you all of this just to make sure that you understand that coal has less percentage of carbon and coke has a high percentage of carbon. High percentage of carbon because most of the non-metals have been converted into their individual gases and left the coal, because gas can easily move out of coal. All right? So we use coke, which is mainly pure carbon. We use limestone, which is CaCO3, and all of this is entered into the blast furnace. The temperature in different parts of blast furnace is different. It's highest at the bottom and it's lowest at the top. The blast furnace is lined with steel and heat-resistant bricks, usually made out of magnesium oxide. Now we have two different taps. One tap hole is for slag, the waste material that goes out, and one tap hole is for iron, which is actually molten in this case, as mentioned over here. Both the slag and iron are in molten forms. Now let's discuss about the other details. Okay. Metals above carbon in the reactivity series. Let's say metals above carbon were potassium, sodium, calcium, magnesium, and aluminum. As an example, we're going to pick aluminum, which is present mainly in the form of bauxite, the major ore of aluminum, as mentioned over here. So what we do is that we use this aluminum along with a molten salt called cryolite. And why do we use cryolite is mentioned over here. Cryolite is simply used to make the process more economical. Aluminum oxide melts over 2000, but if we dissolve it in cryolite, which means it also works as a solvent, don't forget that, that has been a part of past papers. So cryolite acts as a solvent. Also, cryolite reduces the melting point from 2000 to around 1000 degrees centigrade, and that saves a lot of energy and a lot of money. That saves a lot of costs in the fuel that we use to burn in the heating up or the melting of this aluminum oxide. Majorly, coal is used for this purpose. Now, coming to the diagram, you would see that we have a carbon cathode. By carbon, we mean graphite, and we have graphite anodes as well. We have a solution of aluminum oxide in molten cryolite, again the solvent. We have a steel tank lined with heat-resistant bricks, again made out with magnesium oxide. All right. So when the reactions occur at cathode, aluminum ions are converted into pure aluminum by the gain of electrons, hence reduction. At anode, oxide ions are converted into pure oxygen. This one is liquid, this one is gas at this point. All right. The state symbols are not mentioned, so I wanted to make sure the state symbols are mentioned. In this case, the electrons are lost, hence it's an oxidation process. Easy enough. We have been continuously saying that anode oxidation always occurs at anode and reduction always occurs at cathode. Right? Are we good?
Yeah.
Okay. So this process requires still a lot of amount of electricity. Even when we have brought the temperature down from 2000 to 1000 degrees centigrade, it still requires a lot of electricity, and which makes it expensive. Metals such as aluminum has to be extracted by electrolysis, and which makes it more expensive than iron. That's why iron is the most used metal. The process of blast furnace is pretty old, goes back a few thousand years, humans have been using iron more than any metal on the planet so far, and they used it even centuries ago. So that's because iron can be extracted by a blast furnace, and metals like aluminum have to be extracted by electrolysis. Electrolysis is pretty expensive, so we do not opt for this process for any metal unless we have to. The list I was talking about previously, unfortunately, in that list, we need to opt with this method. So these 5 are usually extracted with the help of electrolysis. Then we had carbon. After carbon, we had zinc, iron, and copper that we usually extract with the help of reduction with either carbon or carbon monoxide. So moving on. Alloys. I think alloys are pretty easy. Would you like me to revise it?
No, alloys are simple.
Pretty simple. Mild steel, high carbon steel, stainless steel, copper and its alloys. Yeah, this finishes the chapter. Titration is actually to understand the course of neutralization reaction. Don't forget, neutralization was acid when reacts with alkali, produces for us a neutral component, which is water, plus it also produces salt. Remember, H positive ions from the acid combines with OH negative ions from the alkali to form water. All right. So what happens is that the negative part of the acid and the positive part of the alkali, they combine to form the salt. So whichever salt we're going to produce depends on acid. Right? So it's pretty simple. Hydrochloric acid would give us chloride salts because the negative part is chloride. Sulfuric acid would give us sulfate salts. Right? In the similar way, nitric acid would give us nitrate salts. And the list goes on in the similar way. Phosphoric acid would give us phosphate salts. Ethanoic acid will give us ethanoate salts. Methanoic acid would give us methanoate salt. Carbonic acid would give us carbonate salts. The list would go on. So that has been taught previously, but as that is a prerequisite when we're going to discuss the chemical part of titration. So I wanted to go through that first too. Moving on, what the purpose we do titration is that we are going to either find out the concentration of acid or alkali or the volume of acid or alkali. On the other hand, we can even say we use the same process to find out how many number of moles of acid reacted with how many number of moles of alkali. But remember, as acids and alkalis both exist as solutions in lab, so whatever we are going to do would be done as solutions, hence the term concentration. The technique for carrying out a titration, we need to use an indicator. In this specific case, we're going to use phenolphthalein or phenolphthalein as an indicator. Now, to begin with, we measure out 25 cubic centimeter of hydrochloric acid. We can use a pipette and a pipette filler or filter, right? So I hope you have done that in lab. Have you?
Yeah, we did this one.
Okay. So you can perform the same experiment with different acids or different alkalis or even different indicators. So every time you come up with an experiment, the details about acids, alkalis, indicators, maybe even the concentration of these mentioned substances or their volume can be changed. So this value can always be changed. This name can be changed in any experiment or in any question, which has been done in the past paper a number of times. Now we transfer it to a conical flask. We fill the burette with the other solution. By other, I mean if we are using acid in the flask, the burette must be filled with alkali or vice versa. So if the alkali is in the flask, the acid must be in the burette. How are you going to know which one you're going to fill in which part? So let me tell you, the substance whose concentration is known, because one of these will be the one whose concentration is known, and one of these would be the one that you're going to find with the help of titration. The sole purpose of titration, or the most important purpose of the titration, is to find out the concentration of one of these when you already know one of them. So if you know about the acid, put the acid in the flask and the alkali in the burette. Why? Because the known concentration is always considered for flask, while the unknown for the burette. Are we good?
Yeah.
Okay, good. So take initial reading on a burette and record it to 2 decimal places. How are we going to do that? The readings are usually given in this way. For example, this is 1 and this is 2. So if it lies over here, let's see, if it lies over here, it's pretty easy for you to say it's 1.2. If it lies over here, you can call it 1.4. But if it lies over here, you can call it 1.35. And automatically, as we're talking about 2 decimal places, this would become 1.20 or 1.40. Doing our work like this can give us accuracy up to 2 decimal points. Hence the reason of writing this line. Are we good?
Can you repeat the last part?
Yeah, last part is, if we're going to write 2 decimal places every time, our accuracy would be up to 2 decimal places. That's why they're writing it over here.
After you put the known solution in the flask and you have the unknown in the pipette, what do you do?
Unknown in the burette. This one is a burette. Okay. So what we do is that we take the initial reading, whatever the reading is in a burette, and that's how you measure a reading. The numbers are already graduated on the burette, so you are supposed to just take the reading. Okay, this is 1, and then we have different scales. You know, this bigger scale is definitely 1.5. This one is 2. This one is 1. So this specific reading would be 1.20. This specific reading would be 1.40. What if we have something in between? Like, what if we have the water level over here, the liquid level, whichever the liquid is? Then it's 1, 1.1, 2, 3, 4, 5, 6, 7, 8, and something in between is 1.85. So if it's in between 1.8 and 1.9, we're going to call it 1.85. That's how we work with it. Okay, and don't just write 1.8. It's better to write 1.80 or 1.90 or 1.85 to be something in between. Right?
Okay.
So coming back to it, take reading on the add a few drops of naphthalene indicator. 2 to 3 drops are good enough. Then start adding your alkali until the indicator changes color. Permanent pale pink color will give you an idea that now you need to note the final reading on the burette. Note down the final reading as well. And then you can make the calculations which were discussed before. Now, reading a burette has been explained over here too. For example, you started off with this reading is what do you think this reading is?
That's 2.1. No, 2.2.
2.1. 2.1 is correct. What
Oh
about
yeah,
this one?
2.1. That would be 23.85.
Very good, 23.85.
Yeah.
So that's how we are supposed to work at it. 0 is usually at the top, 50 is at the bottom. Period is bigger than the pipette. Pipette is usually 25 cubic centimeter, and burettes are usually 50 cubic centimeter. Both pipette
So
and burette.
when do you know when to stop letting the unknown solution drop into the flask?
Pretty simple. As soon as you have a permanent change in color.
But that can be inaccurate sometimes.
Yeah, it does. That's why the first titration we carry out, we call it a rough titration. And we definitely try to practice it 2 to 3 more times and we get the average value. Titration is never considered once. We always go for an average of either 2 or average of either 3 titrations. It's better if you take average of 3. All right. The first titration is usually known as the rough titration. The word rough titration depicts that this titration was only used to get an idea where the endpoint would lie. For example, in this case, the endpoint was 23.85. So it would give you a rough idea that your endpoint is near or in between 23 to 24. Next time, you're going to be very tedious about it. You're going to be meticulous. You are going to be very observant that what the exact reading should be. Do it wisely and slowly, patiently for a couple of more times. Take the average so that even if one of your readings is not precise or is slightly inaccurate, that you can take an average to balance it out with the ones that you have taken accurately. All right. So moving on. 23.85, 2.10, volume of alkali adders is 21.75. That's the way we always come up with the volume of alkali. Okay, so here is one more important point, actually a couple of those. You can use various indicators. You can use methyl orange, methylene blue, phenolphthalein, thymolphthalein, any of those indicators, but you do not use a universal indicator. Universal indicator shows 14 different colors or shades of those colors at different pHs. So the color would keep changing and it would change so much that you won't be able to see a clear endpoint. So what we do is that we try to stick with phenolphthalein, methyl orange, litmus, or methylene blue. Whatever we are going to use, it's better you at least remember the colors for neutral, acidic, and alkaline medium for phenolphthalein, for methyl orange, and for litmus as a part of your course. If they talk about any different indicator than that, they are definitely going to tell you the colors as a part of the question. The memorization will only be tested for phenolphthalein, methyl orange, litmus, and the last one is universal indicator as a part of your course.
When are these indicators being used in the titration process?
As soon as we are about to start the period, just before that, we use the indicator, a few drops, like shown in the diagram above.
Oh, so you put it into the known solution.
Yeah, known solution, always.
Okay.
That's correct.
Okay.
So the endpoint of the titration is the point at which the indicator changes color permanently. Here, a word permanently is missing. The point at which indicator changes color does not necessarily indicate the point at which solution is neutral. The pH changes very rapidly near the endpoint, and some titrations, one extra drop of an alkali can change the pH up to from 3 to 11. So You never know an extra drop, what big change can it bring to your entire titration. That's why we always say it has to be done meticulously and, of course, with patience. Right?
So how many drops are you meant to put?
It depends from solution to solution.
Oh, okay.
So you never know. So the best idea, the basic idea behind all of this is to keep a keen observation. As soon as you start changing colors, go very slow, drop by drop, shaking the solution. As soon as there is a permanent change, do not try to use even one extra drop for it. And at the same time, keep looking at the period. So even if you use one extra drop for your confirmation, you have at least noted the final reading. Let's say the reading is 23.85. You have a permanent color, but you're still in doubt. Only use one extra drop, note this reading. If the color change was permanent already, don't use the next reading, use the previous one, this one. And if the color change was not permanent, it changed again, use the next reading. Maybe go for one more drop. Wherever you find it permanent, don't do any more than that. That comes with practice. You understand how to use the drop by drop system and how to note down the proper color change.
Okay.
Right. So this also finishes the titration chapter. What next? So this is an equation they have considered to write the Ionic equation. This equation is about a metal reacting with an acid producing a salt and hydrogen gas. Now, we are supposed to write an Ionic equation about it. Writing an Ionic equation means that all those ions which are a critical part of this equation should be included. And any of the ions which are not a part of the equation critically, we can simply skip those. Which ions are not a part of it critically? The ions who have not changed their states. We call them spectator ions. How do we get to know that? It's pretty easy. We bifurcate the entire equation into all of the ions, especially the solutions into their different ions, and then we cancel out the ones that are same on both sides. Let's take a look. Let's start from this line. This one. Now, reacting with hydrochloric acid, HCl, which we previously wrote like this, as it's an aqueous solution, and inside the solution, the positive ions and the negative ions are separated, so we write them separately. On the other hand, magnesium chloride, which has this formula, is a salt, is also aqueous or soluble in water. The positive ions and the negative ions are written separately. As you can see, the negative ion in both the cases have the same formula and the exact same number, oxidation number, I mean. So we can simply cut this one and this one from both sides. The rest of it is our wanted Ionic equation. Remember, only the solutions are separated into ions. If there is a solid, it would remain as is. If there's a gas or a liquid, it would remain as is. So this becomes the Ionic equation. Simply speaking, spectator ions were chloride ions because they had no participation in the reaction whatsoever. Writing an Ionic equation gives us a pretty good idea. Take a look. Magnesium was present in its original state as a solid with zero oxidation state on the left-hand side, but magnesium is present as a positive 2 ion on the right-hand side. So this method allows us to safely say that magnesium got oxidized in the reaction. Hydrogen has a +1 charge on the left-hand side, while hydrogen present in its native gaseous state has a zero oxidation state on the right-hand side. So we can safely say that it got reduced in the reaction because magnesium lost electrons and hydrogen ions gained them. So writing Ionic equation can give us a pretty good idea of whatever redox reaction, reduction or oxidation happen in the reaction, overall reaction. That's why we write Ionic equation. Remember, for an Ionic equation, the reactants and products are to be written correctly. Of course, that's a part of any equation. We need to balance it too. Of course, that's a part of any chemical equation as well. But the state symbols are very important to mention because that way you're going to differentiate between different states, and you would automatically know that any ions with aqueous sign must have their ions cancelled as spectator ions. All right? So it's pretty easy.
Okay, I kind of understand, yeah. Can you give me an example question? I'll try to answer it.
Sure. I am going to solve the first example myself, and then you can solve the second one. The reaction, such as this one, as given over here, with sulfuric acid, gives us magnesium sulfate as a salt, also gives us hydrogen gas. Magnesium here is solid, sulfuric acid aqueous, magnesium sulfate is soluble in water, hence aqueous, and hydrogen is a gas. First, we need to divide these aqueous into their respective ions. So magnesium is a solid plus H positive ions as aqueous plus the sulfate ions as aqueous gives us the magnesium ions as aqueous. Magnesium are positive 2 ions plus sulfate ions, which are also aqueous, plus our hydrogen gas. Right? Now, if you take a look at it, you would see that we can easily cancel out this one, as this one has the same state symbols and sign numbers on both the sides. Just writing the rest of the equation would leave us with the correct Ionic equation, which is magnesium in its solid form plus 2 hydrogen ions aqueous give us magnesium ion in its positive 2 state aqueous plus the hydrogen gas. That's our wanted Ionic equation. Are we good?
Yeah, okay.
All right. So, talking about the example, you need to solve. Let me write that one. All right. Instead of writing about metals, as we have practiced many equations for metals, let's practice an equation with non-metals. My bad. 2, 2. This one is a gas over here. This one is an aqueous solution. This one is also an aqueous solution. This one, however, comes out to be a liquid. Go ahead. You may annotate it on the screen. The annotations are already turned on, or you may write it on a piece of paper and send it to me WhatsApp, whatever you like.
Yeah, I'm doing it on a piece of paper.
Okay. So after this neutralization reaction, as I've explained, that H positive from the acid combines with OH negative from the alkali, these two combine and form the water H2O. However, the negative part of the acid and the positive part of the alkali, these two combine to form our salt. Let me tell you, salt will always be spectator ions. So for any neutralization reaction on the planet, H positive aqueous plus OH negative aqueous gives us water. Liquid is always the final ionic equation. No matter which acid or which alkali we're going to talk about, the final equation will always be this for an acid-alkali neutralization. Easy. For any acid-alkali neutralization reaction, don't even bother writing the complete equation, cutting out the spectator ions, and then rewriting the ions. Simply write this equation and you will always be correct with acid-alkali neutralization.
Okay.
So my students even memorize this equation, and as soon as they confront a neutralization, acid-alkali neutralization, they don't even bother cutting the ions. They simply write this equation and they are correct always. You can even look marking schemes, you'll find it in the same way. Now, the second one. The second type of equations are usually precipitation reactions. For any precipitation reaction, remember the method remains the same. We take an aqueous solution, we dissolve it in another aqueous solution, which gives us two kinds of salts, a soluble salt, which would of course form an aqueous solution, and an insoluble salt, which we call a precipitate. Remember, precipitate is simply an insoluble salt. As being insoluble, it would settle down at the bottom. We call this one as precipitate. Let me tell you that soluble salt is again the spectator ions. So easier to remember, the soluble salt in this case is the spectator ion, and the soluble salt in this case is also the spectator ions. And the insoluble one is the one that you need to write the equation for. Let's say we combined AgNO3 with NaCl, and both of them are actually aqueous solutions. This one is also soluble in water. NaCl is pretty easy, it's also soluble in water. It gives us NaNO3, which are actually aqueous, soluble in water, which we're going to cut out from the equation. We're only going to consider AgCl, which is a solid and does not dissolve in water, a white precipitate. That actually is not a part of this chapter. I think the last chapter in this unit is about the reactions, the precipitation reactions in lab. I don't remember its exact name, but it was something like that. I think it was the analysis of compounds, the cations and anions. So it's pretty easy. Don't write all of these ions, simply write the ion which is a part of insoluble salt, this one over here, and the part of insoluble salt, this one over here, and you will easily be able to form an equation. Like in this case, Ag positive aqueous plus Cl negative aqueous will make for us the AgCl precipitate, which is a solid, and there you go. You're done writing the equation. Don't even bother to write the soluble salt, cut those parts out, and then get the whole equation. Only do this if you're confused. If you have a good grasp of the precipitation and the neutralization reactions, don't bother cutting and writing out the whole thing. Just simply write your answers. If the working is required, please do the whole thing. And I have seen hardly a paper or two. It's very rare that they ask for you to work down the whole thing. They usually simply ask you to write the answers up straight.
Okay.
All right. So this covers for us all kinds of ionic equations. There's also a third type, but we are already done with this, and that's this one, which is displacement. The more reactive substance, which in this case is magnesium, displaces the less reactive substance, which is in this case are hydrogen ions. So it's pretty easy. Are we good?
Yeah. Can you give me another question to try?
Sure. Let's try. I'm going to give you a couple actually, because I've summarized neutralization and precipitation for you. So let me give you a neutralization question and a precipitation question. So let's say this is going to be a little bit difficult for you, so not this one. First is this one, and for the second one, second is this one. Go ahead and try them one by one.